Have you ever been in a situation where maybe you couldn't find your wallet on your way out, or maybe you lost your glasses when you woke up in the morning, or you spent too much time searching for your keys under all those clothes? Do these situations sound familiar to you? Well, this is why we created Forget Me Not. It is a system that can keep track of your everyday items to help you stay organized. Our innovative solution makes use of camera-based object tracking system, web apps, and advanced voice processing to help you remember and locate your personal belongings effortlessly. In fact, with all of these systems working together, we are able to achieve 80% object detection accuracy in well-lit conditions within the camera view. Our system leverages the machine learning models to detect predefined objects. Well, what does the system look like? The Forget-Me-Not system relies on an easy-to-mount module containing a Raspberry Pi 5 with a camera that is able to both capture and store said images with the ability to process any queries about where said items are. So, how does one use our product? Depending on user preferences, you can either choose our intuitive web app or our voice assistant, Kira.
The software in our final design uses a variety of different technologies, and I think the best way to explain it is to go through the exact steps that happen as the data travels through our server. Firstly, I'm going to cover what steps happen as a picture gets processed and eventually stored in the web server. We begin with our image capture Python script. This script runs on the Raspberry Pi, and its task is to take an image every few seconds and send it out to the server. This time interval is flexibly adjusted depending on the current server load. Our web server running on the Raspberry Pi first checks the credentials of the image request. It then compares the incoming image with the previously sent one. If it's too similar, ML object detection is skipped to save processing power. If it's different enough, object detection runs, generating bounding boxes for recognized items. These results are stored in an SQLite database, making it available for user searches on our website.
One of the areas we most dedicated time towards was improving the ML object detection. Users can choose between either a high privacy mode, that is YOLO V11, running on the RPi, or a high accuracy model, that is Grounding Dino, which runs on a more powerful external computer. We used custom data sets to train these models to improve its performance in indoor environments on everyday objects. We'll talk more about this in the results.
Now that we've talked about the ways our system detects objects, we'll talk about the ways that you can actually search for those lost objects, starting with our web app. Our web app is hosted on the Raspberry Pi and is written using HTML, CSS, and JavaScript. Through it, you can create and log into your account, find or type the object that you're looking for, and search through all of its detected images from the database. Under the hood, all of these actions are done using simple HTTP requests with the web server. As we saw earlier, if your hands are occupied or you don't have a device on you, you also have the option to submit a voice query.
Hey Kira, where's my pencil?
Sure, let me check that for you. The pencil is located on the surface of a white table. There's a textured mat or cloth beneath it.
Similarly to the image capture Python script, we have an audio capture Python script running on the Raspberry Pi, which uses a machine learning model to transfer the query into text and send it to the web server. The web server then uses LangChain, an ML language model, to extract the object of interest. If the user asked, "Where are my sunglasses?" LangChain might output sunglasses as the object of interest. Next, we use vector cosine similarity to find out which object type in the database is the most similar to the object in the query. In our previous example, it might match sunglasses to eyeglasses. When the most recent image with eyeglasses is found, the web server sends the image to GPT Vision and asks it where in the image it sees the object. The web server will then use text to speech to tell the user out loud where the object is. Additionally, our flexible architecture means that if we want to monitor multiple rooms, all we need to do is have any Python scriptable Wi-Fi enabled camera send pictures to our web server, and we will be able to see its images on the website. All you need to do is run the image capture Python script on the camera.
Our system performs well across all benchmarks, from the camera pre-processing, speech-to-text conversion, server response times, and database operations. All of these meet their targets. Our bottleneck for system speed is the object detection model, as it was expected, but it is definitely still within acceptable range. Testing out different models and training them on a mixture of public data sets and our own images got us to meet the 80% accuracy target for predefined objects. Overall, the system performs better than originally intended, but we continue to refine these aspects to ensure that it becomes faster and more efficient, ultimately enhancing the user experience. The system successfully implements core functionalities like real-time image processing, voice-based querying, and efficient storage, which aligns closely with our expectations. The project has potential for broader applications in security, elder care, and home automation. Future development could focus on enhancing model training with bigger and diverse datasets, scaling the system using cloud infrastructure, and refining user interfaces. Thank you.